Hi everyone, my name is Felicia, and today my group and I will be presenting to you about what imaging is and how linear algebra involves in imaging. So this is the agenda of our presentation. So first we will go through what is imaging and how RGB and grayscale images are stored, and then we'll further go about how linear algebra is used in each of the applications of imaging. So the reason why imaging relies on algebra is actually because the images are stored in matrices. So a lot of processing techniques really rely on linear algebra techniques technically. So this is the applications overview. So in image processing, the images are stored in forms of matrices of numbers in a computer. These numbers are known to be pixel values and they represent the brightness of that pixel. So for example, over here we have an image, and as you can see, each pixel has different values. And to make an example, that the pixel here, 0, actually represents black, and here, 255, it actually represents white. So over here we have image compression. This is a process applied to graphic files to minimize the size without disrupting the image quality significantly. Image compression is actually used to save up memory space in your laptop or any desktop computers you have at home. So what it actually does is it kind of pixelates the image quality. You can see the difference of before and after the image has been compressed. It it actually makes the picture kind of duller too. But what image compression does is actually that it doesn't disrupt the quality of the image, as you can see, as they are quite similar, but they're just slightly different. But the quality is still quite good despite the compression. It's just that you won't notice it unless you zoom into the picture. You can see that it's a little bit pixelated here. We'll be talking about the RGB images. They're actually known to be also the true color image. These images are stored using an m by n by 3 data array for red, green, and blue color components for each pixel. For the picture shown, we have the three matrices, red, green, and blue channels. These pixels are usually ranged from 0 to 255, and the numbers represents the intensity. N here will be the number of pixels across the height, and M here would be the number of pixels across the width. And 3 represents the number of channels, and in case here, we have 3 channels, which are the red, green, and blue. So over here, we have the examples of non-RGB images. They technically mean that they have no color. And over here, we have the black and white and the grayscale. So as I mentioned in the previous slides, that black and white, all entries should be 0 or 255, as 255 itself represents white and 0 represents black. And over here with the grayscale, and the difference are that the entries in a grayscale has the values from 0 to 255, and they contain gradients of color. Now we have a little quiz for you guys. Assume matrix A to the right is of dimension m times n. What is the value of the pixel in the picture over here? So the answer is 0, because I've mentioned multiple times that this is a image of a black and white, and 0 represents black here and white represents 255. All right, thank you everyone. This is it from me, and Rajesh now will take over for further applications of imaging.
Hello, my name is Rajesh, and I'm going to be doing image processing part 1, sorry. In this, I'll be converting RGB to a color channel, converting RGB to grayscale, converting the color channels to monochrome, and converting RGB to negative image. Okay, I won't go over this because I have a feeling that Felicia already went over it. Okay, so there are 3 channels, as discussed earlier, the red, green, and blue, and they're in these matrices over here. So our goal is to isolate the red channel from the RGB. The only way to do that is to make the G and B matrix equal to 0. I mean, be 0 matrices. This wouldn't work in grayscale because 0 is the same as black. But in color scales, 0 actually means transparent, which would mean the absence of G and B. So that would only leave red, leaving an impact on the image over here. Okay. Right. Yeah, so as I mentioned before, color images, RGB is a little bit more different than grayscale because it's based on the intensity of color. Okay. All right. And as I predicted, it became red. Okay, so I will also introduce a shorthand version to denote a pixel, and also the color of a pixel. More importantly, color. Well, both of them are as important. So basically what this is saying is it's saying that A11 is equal to a row vector of R11, G11, and B11. Okay. And it will be demonstrated in the next slide. See, so it's a row vector of R11, B11, C11, which is essentially Rij, Gij, Bij. So it's for every vector. So it's for every Aij space. Okay. So this is important, as I said before, because you could literally denote a color by using this RGB scale. So you could say 255 red, 192 green, and 203 blue, right? And by the way, this is a little inaccurate, but I mean, the way the matrix is worded. But anyway, and there's another way to say red too. It's 255, 0, 0, which should make sense given what we did previously to get, because we made G0, B0. It will make sense that that's 0 too. Okay. All right, so I showed how to isolate the green channel, but I purposely didn't show the blue channel. And I think you guys can figure that one out. Okay, so RGB to monochrome. So monochrome is us grayscaling a channel image in RGB. And RGB, I'm sorry, the original image that we'll be using is this one. And over here, we have isolated a red channel, and we have grayscaled that red channel also. So one interesting thing you'll notice is that the grayscaled version and normal, I guess the normalish version, both have the same values, but they have same pictures. How can this be? It's because the color scales and the grayscales interpret the values differently. So for example, the grayscales, they interpret the value 0 as being black, while the red scale interprets the value 0 as being transparent. And the grayscale interprets the value of 255 as being white, while the red scale interprets the value of 255 as being very, very bright red. And you'll see this common pattern occurring, right? Yeah. Okay. So nothing new here. So using this information that we got from the monochrome, we will now try to convert the RGB to grayscale. Okay. So essentially the monochrome is a grayscale of each channel, right? So for example, so in order to find a grayscale of the original image, what you would have to do is add the entries in an index, right? So you do R to find the grayscale entry of 1, you would do R11 plus G11 plus B11, and you would divide by 3. So in other words, you're adding them up and you're averaging them, okay? And that's what's shown over here. And you don't forget to scale over here. That's what's holding it all together. Okay, good. All right, let's do a small exercise. Let's skip the red hexagon and go for the white letters instead. Okay, so the white letters, right? We know that the white value in the grayscale is 255. So we can substitute this V term as 255. And accordingly, C, G, and K have to be 255 also, because 255 is the max that color can be. Okay, so this is the original RGB and this is the grayscale. This is the one we haven't seen yet. All right, so now this is the last topic. We're going to convert the RGB image to a negative. Okay, so the RGB, we already know this. It's a simple formula, 255 minus r, blah, blah, blah. But the thing that we should notice is something that I discussed just now. So if we know that if it is white, if the color is white, then the Rij, Gij, Bij, they all have to be equal to 255. Knowing this, you'll see something that familiar. 255, 255. That's white. And you're subtracting that by the original image. So essentially what you're doing, if we pretend this is the original image, is we're having a white image that's of the same dimension matrix, and we're minusing that by this original image. And you'll get the negative as a result. So that's how it works. And this is the matrix visualization. Okay, so my part is done. And Nixon will now take over for image processing in part 2. Thank you.
Thank you, Rajesh, for the clear explanation on image processing part 1. My name is Matthew Nixon Tan, and I'll be going over image processing part 2. In this slide, we have the overview of image processing part 2. I'll be explaining about maximum pooling, minimum pooling, and median pooling. I'll also be talking about convolutions and also kernel filters for line detection. Okay, so for pooling, there are 3 types of pooling: maximum pooling, minimum pooling, and median pooling. For maximum pooling, we take the maximum value of the sliding window and send it to the output image. As we can see on the right, on the image, we have a sliding window that is highlighted in blue. The maximum value of the sliding window is 10, which is then sent to the output image. The one highlighted in red, we have a maximum value of 12, which then also sent to the output image. This process goes on and so on. For minimum pooling, it is almost the same as maximum pooling, but instead of taking the maximum value of the sliding window, we take the minimum value of the sliding window. So for example, the one highlighted on blue, the minimum value is 0, which will be sent to the output image. For median pooling, we take the median of the sliding window. There's also a thing called padding, which is used to prevent the loss of dimensions. As you can see on the image, there are a bunch of zeros on the outside of the image. These are called zero padding. Here are the results of maximum pooling, minimum pooling, and median pooling. We can use these poolings to emphasize intensity or even change the saturation of an image. Next up, we have convolutions. For convolutions, we multiply each element in the sliding matrix by the corresponding element in the filter. As you can see on the image, we have a filter. We have a convolution filter of 303, 202, and 101. After multiplying each element with the corresponding element in the filter, we then add them all up, which results to get output image of the pixel value. Lastly, we have kernels. Kernels can be used to extract patterns from images, such as edge detection, shown on the right. It can also be used to warp an image or even blur an image. In this slide, we have an example of a Prewitt kernel that is used for edge detection, labeled GX and GY. GX is for horizontal line detection, while GY is for vertical line detection. Here we can see the results of line detection. The top and bottom left are the results of horizontal edge detection, while the top and bottom right of the image in this slide are the results of vertical edge detection. And that is all for image processing part 2. Thank you.
Hello, everyone. My name is Jay Sharma, and now we'll be going into image compression. So here's an overview What you do in image compression is essentially you split off the image into these small grids, and then you normalize those grids. And you find these things called DCT coefficients, and you get this thing called a quantization table. And then you do the DCT coefficients divided by the quantization table, and you store that output using Huffman coding, and then you can get back the original image. So I'll explain what all these terms mean and how it actually works as time permits. So here's an example where we start with this image right here, and then this is one of the 8x8 images from this image, right? 8x8 blocks within this image, right? And so these are the pixel values. This is the matrix that corresponds to that to this image right here. And then what you're going to do is you're going to normalize this by subtracting 128, which is 256 divided by 2. So it's 30 minus 128 is negative 98, for example. And this is the input that we'll now be working with. And so the philosophy is that, or the theory is that any 8x8 image can actually be represented as a linear combination of these 8x8 basis matrices. And so in the upper left-hand corner, you have a completely flat sheet, and in the lower right-hand corner, you have a complete checkerboard pattern. And so as you go to the right, there's more frequency in the vertical direction and more frequency as you go down in the horizontal direction. And so the theory is that these 64 basis images can actually represent any 8x8 grid. And you can find the coefficients for that linear combination using this method right here, which I won't get into too much, but there is a method in discrete cosine transform for that. And so here you can see the upper left-hand corner, there is the magnitude of these numbers is very high. And in the lower right-hand corner, the magnitude of the numbers is very low. And that's because the human visual system is more sensitive to the lower frequencies, which are usually in the upper left-hand corner, than the higher ones, which are in the lower right-hand corner. And now that we have that Y that I just showed on the last slide, we also need the quantization table. So the quantization table is like you start with this quantization table, and then you multiply by some scalar S, depending on how much compression you want. The higher value of S means that you're going to compress the image more. And here's the quantized output. What you're going to do is you're going to do the Y divided by divided by the quantization table. So this right here, each element of this divided by each element of this, and then you take the floor of that. So for example, you do 2 divided by 99, and then you take the floor of that and you get 0. So as you'll see, a lot of these actually end up becoming 0, and that means that we don't need as many numbers to represent this image. And so we only need these numbers. And these numbers can actually be stored using Huffman coding. So this is the same image from the last slide. And we can use this snake-like pattern to unwind all of these images into just a 1D array and a 1D vector. And this vector right here can be stored using Huffman coding. And Huffman coding finds the most frequently occurring patterns in your text, and based on that, it will store your 1D array in less number of bits than you needed before. And so if you get your Huffman code, you use Huffman coding to store that 1D array, and then you can get back the exact 1D array. And then you can use the quantization table. You can multiply that YQ that we had before by the quantization table in order to get Y. And remember, since we took the floor we did 1 divided by the other, and we took the floor, we lost some information, but we get something that looks visually similar as it was before. And then we use this computation right here. I won't get too much into it, but C is actually the DCT matrix that is actually orthogonal matrix in order to get back an image which is not exactly what we had before, but similar. And so over here, you can see that this is what we get back when S is equal to 1. This is what we get back when S is equal to 4 for the 8x8 image. And here is what we get back for the entire image. So as you can see, it visually looks very similar. Thank you.
Here are the works cited. Thank you for listening.